Hello, and welcome to the last webinar in the 2020 Virtual Summer Learning Series for secondary mathematics educators on area model progression from the Indiana Department of Education. My name is Robin Conti, and I am the Assistant Director of Teaching and Learning at IDOE. This slide deck is available for you on the Mathematics Standards page at doe.in.gov/standards/mathematics under Professional Learning. Sixth grade teachers can benefit from both elementary and secondary, depending on how your district is set up at the middle level. In this webinar, we will explore high-quality instructional routines that are aligned to the Indiana academic standards to aid in improving teaching and learning of mathematics for all students. What is important to note here is that high quality does not mean complex. Our goal is to explore resources and routines that do not require a heavy lift for educators to implement. Second, we hope that you will discover for the first time or learn ways to refine your current understanding of ways to integrate the specific strategy into your instructional routine, both virtually and in person. We've collaborated with our digital learning specialists to help navigate remote learning and virtual opportunities to ensure alignment of digital innovation in Indiana. This webinar is a little different than the rest of the series as we are not focusing on a standalone resource, but rather the progression of using area models from kindergarten through high school. An area model is a rectangular diagram or model typically used for multiplication and division problems in which factors or the quotient and divisors define the length and width of the rectangle. You can break a large area of the rectangle into smaller parts to make the calculations simpler. Then add to get the area of the whole, which is the product or quotient. You may notice the division example that the calculations are being performed with friendly numbers. 5 times 100 is an easy calculation and is built on the skill of using base 10 blocks and chunking groups of 10 in an array before this visual model is used. Let's be honest, multiplication and division, especially multi-digit multiplication and division, have historically been taught and solved by following a set of steps and memorizing rules. Area models help make the connection between multiplication and division and place value and area. Area models help develop the conceptual understanding of multiplication and division before the standard algorithm is introduced. Area models are based on the distributive property and allows numbers to be decomposed into base 10 units, and students are able to connect these diagrams to other mathematical calculations to develop their number sets. Area models provide students with a visual representation of the concept required to understand place value and explicitly make the conceptual connection. I know we are all secondary teachers, but hopefully part of the reason we're here is to learn how this all connects K-12. If we look at these two examples of multiplying two binomials, you can see the connection that can be made from simply introducing area models starting in grade 3. Have you ever heard your students say they never learned that? Or they look at you like a deer in headlights when you know the previous teacher taught them a specific concept? If we understand the progression and how it starts, where it's going, our students will no longer look like deers in headlights and actually begin saying things like, I remember that from last year. Think about the concept of FOIL. We still use it, and it's still out there, and it's still being taught. But what if we help students visualize what multiplication of binomials look like? We aren't limiting our students' understanding, but rather opening up the possibilities. FOIL is limiting and merely a trick. At the very beginning stages of learning to multiply, before we even call it multiplication, we ask our students to learn how to make patterns. In lower elementary, we start with arrays, which is simply a group of objects ordered in rows and columns. Arrays are an essential part to conceptually understand multiplication and knowledge application when confronted with more complex ideas that traditionally require a series of steps or rules. Arrays are a springboard for the skills they will need to be successful through high school algebra. Then we move into a hybrid of physical and visual, base 10 blocks. We are going to start getting more abstract with the physical model. This is where we start to support the development of proportional reasoning. Base 10 blocks is essentially splitting our arrays up into chunks of 10, but is much more efficient than using a single unit. This is where we start to build that deep conceptual understanding. Finally, secondary students are introduced to algebra tiles. More than likely, your students may not have worked routinely with algebra tiles. Be sure to go slow to go fast. Begin by introducing or reintroducing what each tile represents. Here, I am using a website called didax.com, which is linked in the notes section. The coloring of the tiles will change slightly depending on the physical or virtual models you use. Here, all of the red of various sizes represent negative values. The small yellow square is a positive unit, the green bar is a positive variable, x, and the large blue square is a positive x squared. Next, explore simple expressions using the tiles. Approach this with flexibility. For example, begin by asking students to model the expression 3x plus 6. Be sure to honor all correct models, regardless of their organization. Students will naturally come to their own conclusions for organization as the work becomes increasingly complex. Possibly begin by showing a model and asking students to write the expression. Because the small units are red, this represents 3x minus 3. If you teach upper grades, be sure to include quadratic trinomials. There is also a great Wolfram Alpha demonstration that visualizes the multiplication of 3 linear polynomials using a volume or 3D model. The link is in the notes section of this slide deck. Asking students to model 2x plus 9 would be a light lift for students, although they may grumble about having to drag 9 small squares over or pull 9 small squares from their bag. But what about 7 times the quantity of 2x plus 9? Display this expression and have students discuss and explore what this means. If this is the first time students see an expression like this, having algebra tiles to manipulate can help focus their thinking. If students are really stumped, ask them to remind you again what 7x means. Even after all this, modeling this expression with algebra tiles will be cumbersome and honestly inefficient. This is where we begin to move from the concrete manipulation of tiles to a more abstract visual, the area model. Here, students can simply draw a rectangle that has been partitioned. You may want to use this as an opportunity to review tape diagrams as well in the earlier grades. Remember, tape diagrams are visual models that use rectangles to represent the parts of a ratio. Here, you may choose to simply partition inaccurately. Next, place the 7 as one length and partition the 2x and 9 to represent the pieces of the other length or width. As a side note, I had my students put the plus or minus sign in front of the term on their models. Obviously, the plus sign is not required, but is helpful. Now we have created a simple area problem, which is a concept students have been working on for years. Students will find the area of each partition section. The 14x and 63 are referred to as partial products in the earlier grades. To find the total area of the rectangle, students simply find the sum of the partial products. One last tip here, use this language with your students. We do not need to water down vocabulary for students to understand. As we progress through the grades, the introduction of negative numbers can cause confusion, as negative numbers are not associated with length. For this reason, the use of area models to aid with conceptual understanding is often referred to as the tabular method. Try this yourself. Grab a sheet of paper, pause the video, and simplify the expression 4 times the quantity of 8x minus 5 using the tabular method. What about this expression? Students can not only decompose the expression negative 4x plus 7, but they can also decompose the 14 to make the problem more accessible. Again, to obtain the simplified expression, students simply add together the partial products to get an equivalent expression of negative 56x plus 98. Be sure to model and explore all of these options. Remember to go slow to go fast. Students are making connections the entire time. How do your students respond when introduced to polynomial multiplication for the first time? Even the 10th or 100th time? Even simply two binomials? This can be a stressful leap for students. Using area models or the tabular method can help students make connections to prior learning and reinforce their conceptual understanding. This in turn will help students become fluent and flexible in their learning of multiplying and eventually dividing polynomials. Again, if your students are unfamiliar with algebra tiles, you may want to provide an opportunity for exploration in the context of learning first. Let's start with multiplying the expressions x plus 2 and x plus 3. If you use a site like Didax, there is a corner frame option to help students organize. The introduction using the concrete tiles allows students to physically manipulate, even virtually, the tiles as they gain understanding. Students begin to fill in the mat or space, making efficient use of the tiles. Finally, students can count each type of tile and write their expression. In my own experience, I found students needed this opportunity for physical manipulation several times to really get the hang of it. In this learning process, students begin to make sense of what is happening. Using a more abstract model can be very helpful as well. Given the opportunity, students will notice that like terms can be found on the diagonal. This is a great observation to capitalize on when factoring trinomials and reversing this process. Be sure to explore problems using negative numbers as well. For upper grades, include coefficients on the x terms. Giving students the opportunity to connect this new learning to prior understandings will strengthen and solidify their current understanding. Let's explore completing the square in this visual manner as well. Why is completing the square useful? The most common response? It helps students turn a quadratic function from standard form to vertex form. So why is that useful? Students can then use their knowledge of transformations to graph easier. Students can also solve quadratics by taking the square root every time. Maybe these are valid and the only reasons. I disagree, but let's pretend they are for now. Do these reasons really matter if students can actually complete the square? The answer is a resounding no. Do these notes look familiar? I have worked in 3 states in my career and 5 high schools. I have worked with countless other schools since working for IDOE. Notes like this for completing the square are commonplace. They are procedural in nature, have no opportunity for students to connect their learning to prior understandings, and serve no purpose to the student. Let students explore first. If the teachers in previous courses have utilized algebra tiles, students will draw back on that knowledge quickly. If not, give them time to explore. Again, we must go slow to go fast. Have students model the expression x squared plus 6x plus 9 with algebra tiles. If you don't have any, simply have them draw the representation of them or use a virtual method. Remember, accept any correct model. Organization is not a must initially. Next, ask students to arrange the tiles to make a square. This may take students time to explore, especially the first time around. Surprisingly, students catch on quickly after the first success. Does it matter if the square they created looks like this or like this, or another version? Not initially, but we really should work towards this first representation. Finally, ask them to write an expression for the length and width of their square. Students will see x plus 3 and x plus 3 as the length and width. Students have just factored the expression x squared plus 6x plus 9 without knowing it. The factored form can be written as the quantity x plus 3 times the quantity x plus 3, or equivalently, the quantity x plus 3 squared. Try this with several perfect square trinomials. Be sure to ask students to share their noticing and wondering along the way. Next, let students explore a different way. Allow students the opportunity to discover how to determine the constant term here through multiple examples. Maybe give quadratic expressions such as x squared plus 25 as well. What assumptions will students make? By providing the manipulatives, either tangible or virtual, students are able to check their assumptions and easily pivot their thinking when needed. Through this process, students begin to realize the process of completing the square because they are completing a literal square. Use negatives as well. When they fill in the units, the discussion that they need to be positive will happen naturally. Why is that? Is this always the case? There is an abundance of opportunity for rich discussion through these types of explorations. The new expression students will arrive at here is x squared minus 10x plus 25. The length and width of this square is each x minus 5. The factored form of x squared minus 10x plus 25 is the quantity x minus 5 times the quantity x minus 5, or the quantity x minus 5 squared. At this point, students more than likely have discovered the pattern. They will recognize that they will not be able to make this a square because they can't split the x's equally in half. Bingo. That means step 1 has been discovered. In this case, we can move from the concrete to the more abstract visual. What would it take to complete this square? If students truly have discovered the pattern, they will know to square 3.5 to complete the square. So then the length and width of this square is x plus 5. Continuing through this line of thinking, you can build in to actually solving quadratics, graphing quadratics, and deriving the quadratic formula. As you have seen, using algebra tiles to make student thinking visible has many places in our content. Using algebra tiles to support solving equations is another great use, not addressed in this webinar. A great resource to help you with planning is the Math Framework. The Math Framework offers the looking back and looking ahead sections that shows you the vertical alignment of standards. Utilizing this part of the framework can help you choose tasks that best fit your students' needs and recognize the prior knowledge needed that can be used to build on the understanding of a grade level target. When thinking of working with area models, in modeling using tools, process standard 4, model with mathematics. They describe mathematically proficient students as those who create and use a variety of representations to solve problems and organize and communicate mathematical ideas. This points to the idea that we are reaching beyond the standard algorithm and giving students purposeful practice using a variety of models to reach the same goal. Students will be able to make connections as they progress through school and draw upon these connections as they learn new content. Also in modeling using tools, Process Standard 5. Use appropriate tools strategically. Mathematically proficient students are those who consider the available tools when solving a mathematical problem. They are sufficiently familiar with tools appropriate for their grade to make sound decisions about when each of these tools might be helpful. This is a great example of students being able to demonstrate efficiency. If a student loves to use algebra tiles to multiply polynomials, but are still reaching for those cubes and tiles when they are asked to solve more complex problems, is that good? In seeing structure and generalizing, Process Standard 7 describes mathematically proficient students who look closely to discern a pattern or structure. Area models and the tabular method are all about patterns, and that starts back in kindergarten. Understanding patterns in math is required for students to be able to proficiently organize mathematical information. Just like the process standards, we could argue that all of NCTM's 8 effective teaching practices are embedded within the area model progression. Using and connecting mathematical representation stands out as area models and the tabular method provide students with a concrete representation that leads students to develop conceptual understanding and be able to connect to that the procedural skills that follow. Area models support productive struggle in learning mathematics. Area models essentially are helping students create their own algorithms. Students are given opportunities to grapple with ideas and relationships that surround area models. When students are given ample time to work through new ideas, they will gain a deeper understanding of the content. Finally, building procedural fluency from conceptual understanding. Area models provide students with opportunities to manipulate concrete materials to help them make sense of the math. Starting with the concrete physical models will help students build their toolbox of methods that will instill a sense of number flexibility as they continue to add to their toolbox. Expanding further on the last point, procedural fluency refers to knowledge of procedures, knowledge of when and how to use them appropriately, and skill in performing them flexibly, accurately, and efficiently. Fluency builds from initial exploration and discussion of concepts to using informal reasoning strategies based on meanings and properties of operations to the eventual use of general methods as tools in solving problems. Each school year brings its own unique set of challenges. The 2020-2021 school year will be no different. It is imperative that we focus on the acceleration of learning for our students, which is loosely defined by teaching and learning more than 1 year's amount of content in a single year. In order to do that, we must make a commitment to teaching grade level content while strategically and intentionally drawing on and reviewing prior content. In the notes section of this slide, there is a great resource from the New Teacher Project titled TNTP, Learning Acceleration Guide. This guide offers meaningful support and research surrounding learning acceleration. I've also included a document released by the Council of the Great City Schools, which is a national organization providing a network for school districts sharing common problems to collectively address new challenges in order to deliver the best possible education to our youth. The document titled Addressing Unfinished Learning After COVID-19 School Closures is intended to address the challenges of prioritizing instruction to address unfinished learning. When thinking about the need for accelerating learning, what better way to really learn and understand the progression of mathematics K-12? We need to be intentional with our instruction to prepare our students for the evolving complexity they will experience in math. Vertical alignment to all math concepts is essential to this task. We have to know where students are coming from and where they are going, and how all facets are connected. It is nearly impossible to teach every missed concept while teaching current grade level content, so it is necessary to prioritize the concepts and skills that are essential in helping students access rigorous grade level content. So how do you identify essential learning to accelerate learning? Ask yourself these questions to help find the most important content to teach. Does the content extend from earlier units and grade levels? If you're using the area model progression, it most definitely will. Does the content extend into future content? I hope I was able to show you that area models progress into each grade level, building a deeper understanding. Does the unit help students deep conceptual understanding and subject area expertise? The area model progression essentially is learning conceptually before procedurally. Is this content that students need to know right now in order to continue learning grade level matter? Asking these questions will help you determine the significance of your lesson and identify key instructional priorities for accelerating learning. Area model simulation is a PhET interactive simulation. If you're not familiar with PhET, it is a project at the University of Colorado Boulder that creates free interactive math and science simulations that are research-based and engaging for students that gamify math or science concepts through exploration and discovery. This link is to the area model simulation. You can create ones from scratch, including partial products and factors, or work through pre-made area models. Didact's Virtual Manipulatives is a free resource full of digital manipulatives, including Unifix cubes, 10 frames, Reckon-Rex, base 10 blocks, place value disks, and algebra tiles. Braining Camp is a great resource for virtual manipulatives, but unfortunately is not free. The pricing is reasonable though, and I think worth the money. Toy Theater is a virtual manipulative website I've mentioned and used before. It's a good free resource with many different manipulatives to support modeling abstract math concepts for deeper conceptual understanding. Thank you so much for joining me today. You can scan the QR code by opening your camera and holding it up to the screen or another QR reader app. You can also click the slide deck to fill out a short survey. Check out the notes on the slide deck for the link to the presentation. My contact information is also available. Feel free to email me or tweet at me anytime. I'm happy to help. Thank you so much for your time and dedication to Indiana students.